In this video, we're going to take a look at a maximum and minimum turning point question that's a little bit unusual or different to what we would have seen previously with our polynomials. In this question, we're looking at 4x plus 4 all over x. Now that's quite different to what we would have seen before, but it is a straightforward differentiation question if you are able to use your indices laws. So the first thing I would do here is not differentiate it. I would actually rewrite this out as y is equal to 4x plus 4x to the minus 1. Now I'm able to differentiate it because it's all in the powers that I need to work with when I do my differentiation, and it is a nice straightforward question from here. dy dx is equal to, and then I'm going to multiply down by the power 4, take 1 off the power, x to the 0, multiply down by the power minus 4, x to the power of minus 2. Minus 1 minus another one gives us minus 2. Tidying that up a little bit more, I'm going to get 4 by 1 minus 4x to the minus 2, which is 4, minus 4x to the minus 2. Now, the question was to find the turning points. What we know and what we can say about the turning points is that dy dx is equal to 0. So the first derivative at the maximum and the minimum is going to be 0. This is my dy dx. So I'm going to say that dy dx, which is equal to 4 minus 4x to the minus 2, that's equal to 0. And I'm going to try and solve that now. When I look at this and I try to solve it, it's a little bit difficult for me to do that in my head when I see x to the minus 2. So I'm actually going to use indices laws again, and I'm going to change that to the power of a minus to the fraction. And that's something that's in the log tables, something that you would have covered when you did indices. So then I'm going to have 4 minus 4 all over x to the 2 using this rule over here. And that's all equal to 0. Next thing I'm able to do is I can do two different things. I could either multiply through by x squared to get rid of the fraction, or I could say that actually the number 4 is a common factor here. So I can take 4 out and factorize it, and I'd be left with 1 minus 1 all over x squared, and that's equal to 0. Now what I can do is divide everything through by 4, and I'm going to be left with 1 minus 1 all over x squared is equal to 0. I still don't want that fraction there, so what I'm going to do is multiply everything through by x squared. And if I do that, I'm going to have x squared minus 1 is equal to 0. At this stage, there is two different ways that you can solve this. One way is by using the difference of two squares, because 1 is a square number. If I do the difference of two squares, I will see that that factorizes down to x minus 1, x plus 1. I have two things multiplied together, it gives me 0. That means 1, or both of those things are equal to 0. So either x minus 1 is 0 or x plus 1 is 0. When I continue on to solve that, I'm going to have x is equal to 1 or x is equal to minus 1. Notice how I have two different x values, two turning points that I need to talk about. The preference I would have is to use this method because you can clearly see why there's two. The other way you could do this is you could add 1 to both sides, and you're going to have x squared is equal to 1. And I'm going to get rid of the square by square rooting it. And I'm going to have x is equal to the square root of 1. If I am to get the square root of 1, a lot of students would be tempted to say that the answer is just 1. But if you look, when we did it this way, we got two answers. And when you do it this way, you will also get two answers. But it's sometimes forgotten that the square root of 1 is plus 1 or minus 1, because you can square plus 1 and get positive 1, and you can square minus 1 and get positive 1. And that's something that's often forgotten by students. So I'd have a preference for using this method here. Once I have my x coordinates, the next thing I would need to find is my y values. And I can get those because we had a formula for y in terms of x. So I'm now going to plug in each of them. I'm going to have x is equal to 1 and x is equal to minus 1. And I'm going to plug them into this formula that literally gives us y, because it says y equals this and it depends on x. So let me take out the x's here and I'm going to put in my 1. If I do that, I'm going to get 4 plus 4. So I'm going to get y is equal to 4 plus 4. Y is equal to 8. That coordinate is going to be 1, 8. That was nice and straightforward. The next coordinate then, I'll do the same thing. Y is equal to 4 by minus 1 plus 4 divided by minus 1. And what I'm going to get is y is equal to minus 4. 4 divided by minus 1 is minus 4 as well. So I'm going to have y is equal to minus 8. So that one is going to be minus 1 minus 8. At this stage in the question, I have found 2 turning points, but I don't know which one is my maximum and which one is my minimum. And I have to be able to show that I can determine which one is the maximum, which one is the minimum. And how we do that is we look for the second derivative. And what we know is that if we get the second derivative and we plug in the x value, if it's greater than 0, we have a minimum. And if our second derivative is less than 0, we have a maximum. It's a maximum. So I need to get the second derivative. So I'm going back up to where I got the first derivative. And this is why it's just so important that you're keeping track and you're using the correct notation for your dy, dx, for your y, for when you sub in your x, for when you find out your y, and so on. The notation is really important so that you can find things quickly and that other people can read your work as well and follow along. The second derivative, this notation, means we have to look for the derivative of the derivative. So we're going to get d2y dx squared. If I get the derivative of this, I'm going to have that the constants go to 0. I'm going to multiply down by the power, so I'm going to get plus 8, x, take 1 off the power, becomes minus 3. That, if you remember your indices laws, could be rewritten as 8 all over x cubed. After that, we have to test each of the x values that we got, because this says that d2y dx squared still depends on the x coordinate. It still depends on x. So I'm now going to test each of my x coordinates, and those were x is equal to 1 and x is equal to minus 1. So I'm going to take this and bring it down here and test d2y dx squared with each of those. So if I do it for x is equal to 1, I'm going to have d2y dx squared is equal to 8 all over 1 cubed, which gives me 8. That is greater than 0. So we're going to have that 8 is a value greater than 0. Therefore, that value works out to be a minimum. In this scenario, I have the same setup, so I'm going to go d2y dx squared is equal to 8 all over minus 1 cubed, and what I'm going to get here is minus 8 as my final answer, because minus 1 cubed is minus 1 by minus 1 by minus 1, and what the three of those together will give you is minus 1. Divide that into 8, you get minus 8. And minus 8 is a value less than 0, and we would say therefore that is our local maximum. So the maximum point is minus 1 minus 8, and when we subbed in 1, we got a minimum, and our minimum therefore is 1, 8. So it's not always what it seems. This is telling me that the minimum point where the curve has a minimum, it's at 1, 8, and where it has a maximum is at -1, -8, which is counterintuitive to what you might have thought previously. So watch out for that. Make sure that you are checking the d2y dx squared. Is that greater than or less than 0?